Hi everyone. Thank you for the opportunity to be part of the CCDC Student Day once again. It's going to be my last one, sadly. My name is Frade, and I'm a Pfizer and CCDC sponsored DPhil student at the University of Oxford. And I work with Professor Richard Cooper in the intersection of machine learning and chemistry. And today I'm going to be presenting some of my latest research. Yeah, there you go. So I'm going to introduce a little bit the project motivation. So cheminformatics is the multidisciplinary field that brings together computer science and information technology, and then uses their tools and strategies to investigate problems in the field of chemistry. And one of its main areas dedicated to the study of structure-property relationships that we can then use to predict molecular properties from molecular structures. And indeed, cheminformatic models are very appealing because they promise to deliver detailed information about compounds in a fraction of the time and resources required by traditional experimental methods. However, there is a general concern that the majority of published models do not meet the requirements for a reliable practical use. And so my PhD project addresses some of the cheminformatics predictive and modeling challenges through the study of a series of solid state material properties. And also, as part of my project, one of the goals is to exploit the existing experimental data contained in the CST and then build reliable predictive models for each of those properties that I study. So here is the overview of the entire project. The work is organized into 4 main parts, and if you read the titles, you can see how one might naturally lead to the other. So first, we try to understand this problem of why models are so promising during their production and evaluation, but then when you take it after their deployment and use it in another context, they don't seem to perform up to their standards or up to their expectations. So then we try to address these limitations by testing whether there's room for any chemical dataset improvement with descriptor design. And despite the small improvements, the approach does not provide us a practical solution. And so instead, we went off and designed a couple of strategies that try to increase the practical value of these limited performing models. So the models are still not great, but we try to make the most out of them with these 2 tools or filters. And then finally, when we can operate the model in a way that we trust, we attempt to derive some chemical insight here in part 4, and then apply it to guided molecular design and other types of applications. So for my last CCDC Student Day, I will walk you through something called the generalizability tool. And yeah, so the literature has shown that models do not generalize indefinitely across chemical space. Models are built from a particular data set, a particular collection of molecules, and it's chemical content that will determine the regions of chemical space where the model holds its predictive power. So during model construction, it is standard to have a data set that you then randomly split into training and test data. So the first one is used to fit the model, and the other one is used to evaluate its performance. This is the standard practice when you're building a model. So if if you project your training data in chemical space, you may end up with something a bit like this. This is just obviously a picture just to convey the idea that I want to put across. So this is chemical space. If you were to, project your training data, you might get something like this. Then it's standard to process your training data, where you may discard some outliers and you do a bunch of other stuff. And eventually you end up with a training set that occupies a well-defined region of that chemical space, as you can see here. And so then you can carry on with model fitting, where you learn the class boundaries, and this region that you can see will represent the focus of your model in chemical space, or its applicability domain, if you wish. So now it's time to evaluate the model, and you have your test set for that. And when you evaluate the performance of your model, that performance is what you expect your model to operate at in any case that you apply it. So the caveat here is that your initial test is before that, your initial test, the test set is very similar to your training data, right, in the beginning, because of how both initial sets were produced. So that means that the majority of your test set will land within the same region of chemical space. And however, after you deploy the model, test sets have a much different structure, and they may appear a bit more like this all over chemical space. So this is the moment where you have the model, you take it into production, you take it into a completely different context, and you just start using it. Your test set may look a bit more like this. And most points, as you can see, may lie outside the designated region or applicability domain of the model. And you cannot expect the model to generalize to those points with the same performance. So this is one of the major reasons of why models do not perform as expected after deployment. And so we implemented the generalizability tool, which is basically a wrapper designed to restrict the model to regions of the chemical space where it holds its predictive power. So in other words, this is a filter that, given any test set like this, it can help you identify the points that lay within the applicability domain of the model and the ones who don't, and then filter those down. And so this way, you just make sure that whatever will be handed to the model, it's within its applicability domain, and then you can expect the model to perform as expected. Right, so from the machine learning point of view, you can frame this problem as an outlier detection task, and you can look at the generalizability tool as an outlier detection method. So how did we implement this? Well, this is the kind of plot that we were getting in the first step. And basically, there's different types of outlier detection methods described in the literature. We tried a few, and for this particular problem, I'm gonna present, it doesn't matter what this data is, but we here decided to go with distances in high dimensional space, which is a way, that has been implemented to detect outliers. And so that's what we've implemented here. But what I want to show you, and what I would like you to focus on, is the trends. So first, we have a training set, and we need to calculate the center of that training set, which is the hypothetical point that is closest to all training points at the same time. And so we calculate that, that is called the centroid of the training set, and that's what we calculate first. Then we move on to the test set, and we calculate the distance between each test point to that training centroid. So you then have a feel of how far is my test point to my training data. Because distance can be seen as a measure of how likely your test point is to belong to that training distribution. Right, so at the end of the day, you will have a test set, and each point will have a distance associated with that. Its distance to the training centroid. And then what we do to get this kind of plot is we go to the test set and say, well, I want all the points that are within a distance to the training centroid up to 7.5, and you get a collection of points. Then you want all the points with a distance up to 10, and you get this collection of molecules, and so on, 15, 20, and so on. And so each of these points kind of represents a collection of molecules that you use to evaluate the model. And as you can see, the bigger the anomaly content of your data set, you can see kind of like a decrease in the performance of your model, right? Which means that, well, this method is strong enough, or it's appropriate enough to find outliers in our test set, and those outliers correspond to, you know, they have a relationship with the performance of the model. And so what we can conclude from this plot is that the method is able to successfully capture outliers, because then again, it depends on your data set. That's why we've implemented several outlier detection methods. This happens to work well for this particular data set. And if we move on to another data set, we would have to try a bunch of other methods and see which one works the best. Then, how do we know that the tool works well for a given data set? Well, you already see that there's a good trend here, but now you have to move on to step 2. And so first here, we build a predictive model and we calculate the training centroid. That's from our training set. And then what we can do is we go to our test set and sample it 5 times. And you can sample it 10 or 2 or whatever you want, but the idea is that you sample it. And then you calculate the accuracy of that sample, the accuracy that the model has on that sample before filtering your outliers and after filtering your outliers. So before using the generalizability tool and after using it. And if there is a significant increase or improvement that is also consistent across the 5 samples, and you can see here that there's always a consistent improvement, it means that the generalizability tool works well for your data set. So you can see here that before using the generalizability tool, you get a mean accuracy of 84%. But if you indeed use the generalizability tool, so you filter out the outliers, you will have your model performing up to its expectations. So if you look at the 90% is exactly what you see here, is what the model is expected to work at when there's very few outliers. And then just to say that, well, this generalizability tool has some parameters. and they can be tuned for different outcomes. So for this particular one, you always have to set an anomaly threshold to define, well, this is a distance that below that, all the points are considered inliers. After the outliers, therefore, I will not look at those. And obviously there's a trade-off. Well, this is a filter, so the better you want your answers to be, the stricter the filter has to be, and in turn, the less answers you will have access to. And we built this generalizability tool with the data that we had, but we envisage, a much better not performance, but this method is it works a lot better in when you're trying to perform tasks like virtual screening, especially of diverse libraries. So the idea here is if you take a model into production, let's say to a pharmaceutical company, and you have millions of compounds to screen through in early stages, you can imagine that maybe that library will have something that it's more peptide-like. So you would have big molecules, you would have small molecules, you would have all kinds of molecules. And if your model happens to be trained on small molecules, the idea of this generalizability tool is to then, use the model across the library. But when it looks at peptide, it says, well, this peptide, this molecule is a bit different to what the model has been trained on. Therefore, I don't think it will generalize to that. And so I will not, consider it for my model at this time. And yeah, so it was a short presentation. Finally, I just want to thank to my 3 supervisors and obviously the sponsors as well for making this project possible. And thank you for listening.